Thanks so much, Jen. So uh, I think that, yeah, those questions you raised at the end are an excellent starting point indeed for a wider discussion. I think of the, yeah, maybe challenges that we face doing this kind of work. So maybe to kick us off, we have a question from someone who signed up for this workshop. So they were asking a kind of more fundamental question just about this enterprise, I think. So they asked, what kinds of plausible assumptions could we take to explain similarities and differences between human and model behavior? So how do we populate the hypothesis space? So are we taking different models as a hypothesis generator, or are we getting our hypotheses from somewhere else? I'll let one of you just jump in, but if you
I
could do
can
some
try to.
clarity on that, I could also kind of like riff on that myself. I'm just reading the question, but
I mean, I don't know if that's what the mysterious question asker had in mind, but we can definitely take hypotheses from cognitive science as the basis for this evaluation. That's kind of what we've been doing with the reasoning study that I mentioned before. Um, so there's this like extremely elaborate theory that Johnson Laird came up with for exactly how we construct those mental models in our heads that we reason over. And that theory has a lot of interesting moving parts and hyperparameters that you can fit to individual participants that have very different levels of skill at cognitive reasoning, logical reasoning. You could also fit them to AI models. Uh, so I guess a sort of it can take this individual differences paradigm to an extreme and include like ChatGPT in your set of subjects. Maybe other people have other ideas.
Right. So I guess I can talk a little bit about the kind of hypothesis we can propose from social cognition that can help us to evaluate social intelligence. So this is maybe like a misconception, kind of misunderstanding about what social intelligence really is. So when you talk about social intelligence, you think about how you understand people, how you interact with people. It has nothing to do with the physical world, but that's actually not totally correct. And there are hypotheses in cognitive science showing that you do need to understand the fundamental aspect of the physical world in order to really understand people's actions and their mental states and how you can interact with them in the physical world. So we do use those kind of hypotheses to generate stimuli in our benchmarks for AI models that require you to have a basic understanding about physics. So for example, to estimate how costly it is to pursue a goal in this animation I show you, you need to be able to estimate the physical environment, generate a plan, and then estimate the cost for the agents. And if you do not have that kind of capacity, you cannot pass the test. And indeed, that's what we found. So if you train an end-to-end model that only fits the trajectory patterns in the training data, but does not have fundamental understanding about the physical world, they fail to generalize to a scene type. So I think that's probably like one example specifically for social cognition where you can get some additional insights and hypotheses from cognitive science and to create benchmarks and create better models for AI.
Yeah, I guess I'll just add on to what everyone else has been saying. Like, I think, yeah, the hypotheses should be coming from kind of cognitive perspective. I see the models more as like a convenient implementation that, we can't, take a human and modify its inductive biases or, do these manipulations that we can more straightforwardly do with models. So I see as models as like a convenient tool for testing these things, but I think the kind of top-down design of the experiments and the theories that we're testing needs to come from kind of cognitive theory.
Absolutely. That's a really great set of responses to that. So we have a question from Isabel. Isabel, do you want to unmute yourself and ask your question?
Hello, hi. Yeah, thank you so much for really great talks. I had a question about the first talk, like with regards to like generalization. So like, sorry, can you hear me or?
Barely. Yeah, no, I think it's okay. Yeah, I'll just make an effort.
Sorry, yeah, my mic isn't great. But yeah, I was wondering, like, I think you mentioned how language models are becoming like less and less human-like as in like transformers of like longer working memory than people, etc. Yeah, that was really interesting. Like, could you talk more about that? And also, do you see any like impact of that on reasoning capabilities? I was just curious. So thanks.
Yeah, so I think that the fact that language models are better able to predict the next word than most humans is not that surprising if you consider that they know a lot more than most individual people, right? They're trained on trillions of words from anywhere in the internet. So that also, just in terms of the facts that they are aware of, they're just like in a much better position than a person. And then you have the working memory situation. So the fact that people often repeat themselves and texts repeat themselves, but as a human listener, you're not able to verbatim remember the exact phrase that the person used. So you just remember some semantic gist of it, maybe. But the language model is able to just copy what the person said, 30 minutes ago. And then you have collocations that people are just very likely to use this exact 7-word phrase, and the language model can just memorize that. But humans are just not as good as memorizing specific sequences of words, so we have to store some, again, gist of that. So these are just like off the top of my head 3 ideas for why language models that are trained on trillions of words are much better than humans at predicting the next word. Does that answer your question?
Yeah, I guess like additionally, I was curious, like, do you see any like impact of that on reasoning capabilities, like versus humans?
So we actually have the study that I mentioned on reasoning is kind of in progress. So far, the kind of tentative results is that the reasoning capabilities are different from human reasoning capabilities, but are not that great either. And you need to, just from reading other people's work, you need to do a lot of tricks to get the model to reason in acceptable ways, and even the models that are trained on trillions of words are not able to reason as well as a trained expert, let's say. I don't know if I can identify kind of a clear connection between that and the fact that they are superhuman in terms of predicting the next word, but that's a good thing to think about.
Maybe expanding on that too for our other speakers. How do you think about, so this idea that people, like this idea from cognitive science of like maybe it's related to an hour never bottleneck kind of idea where we're having to process information online and are kind of constantly having to chunk things in order to retain traces of it under these constraints we have. Is there a way to like build a model that is scaled up in the same way as transformer can be? So I guess the question is like, we can build toy models that have these really specific hypotheses about what people may be doing, like a model where you explicitly chunk in a hierarchical way. But like, how do you bridge the gap between a hypothesis like that and the kind of like full-blown capacity of a model trained on, like as much text as GPT is?
I can jump in and talk a little about. So I think my general thought is to have modular design for your system. So again, like I'm not the expert in language, so I will talk about in domain of social cognition. So I've mentioned that to also understand social intelligence, you need to understand some other things. You need to have visual intelligence. You need to have physical intelligence. You need to have the idea about what word model is, right? You need to have the capacity of plant in a physical environment. So all these different abilities can be separate models, and each of them can be maybe a transformer or maybe some kind of large neural net that you can train on a lot of data. So you can train a lot of data, train, for example, a neural net on a lot of data to acquire a word model, say, and that can be your knowledge about the word. You can train a lot of and you use a lot of data to train like a policy, a general policy that can allow you to plan in different scenarios, and that can be your capacity to plan in different physical environments. Combining them together, you can then have a general kind of inference algorithm that can allow you to understand other people's mental states. So I think that could be one way to basically combining the capacity of learning from a lot of data using a large model, but also having some kind of cognitive architecture for your model.
Yeah, there's also, I guess, kind of analogous work in language with like building like recurrent neural network grammars or like the structurally supervised transformer models. I think, yeah, those are really exciting kind of architectural developments that can help us test new hypotheses. But I think one of the big limitations there is you need like labeled data, like parsed data to train the models in a lot of cases. And so I think then the data becomes a big limitation. But yeah, the modularity, I think, is a great kind of direction forward.
Yeah, and to add on that, I think people usually think having a model that has the same kind of limitation as human have is a bad thing, but it's not necessarily a bad thing. If you want to, for example, really understand what people are thinking about, given the current certain context, and how you can maybe help them to make, for example, correct their mistakes. So I think even just to fit a model that has the similar kind of cognitive limitation, it also has its own value.
Yeah, so maybe as a final question to wrap up, I think we have another question in the chat. Guangyan, do you want to read your question? And unmute. Otherwise, if you prefer me to read it, I can do that as well. Okay, cannot unmute right now. Okay, very good. So, as we keep scaling, and I guess in the case of language models, we may already be reaching something that predicts the next. I mean, we already are reaching something that predicts the next word better than people do. And I guess this is possibly true in other domains as well. We may eventually get to a social cognition model, for example, that can predict, I don't know, like beliefs and desires better than people can, hypothetically. So I guess the question is the relationship between that kind of scaling and these other biases. So the connection between, I guess, like performance, which can exceed human levels and all of the things that you might think come along with it. So are those biases only kind of an artifact of human, I don't know, like linguistic capabilities or something, or is there some other way we might explain those biases, like that come from a different mechanism, I suppose, is the way that I'm interpreting that.
I have some vague thoughts about this. So I guess one thing that I wouldn't necessarily interpret the fact that language models can predict the next word better than humans as super intelligence or them being more intelligent than humans. I think that most of the cues for predicting the next word are actually just can be based on memorization, and they're not necessarily what we would associate with intelligence. But it could also be that they're more intelligent. Just that I wouldn't necessarily conclude from the lower perplexity that they are intelligent. The other thing is that, yes, to some extent, the biases that we have in reasoning, for example, the most plausible explanation for those biases are the heuristics that we use that are due to limited working memory capabilities. So I think it's quite plausible that language models could reason without those limitations. And I think that maybe the fact that language models, for example, seem to be able to consider more parsers of the sentence in parallel than humans are. Again, it's not specific to language models. Like the parsers that we had 20 years ago are also better parsers than humans in some way. Just like, so the heuristics that we have to use because of our limited resources are not necessarily going to affect language models in the same way. We do, however, for some reason, yeah, again, this is like very preliminary, we do find that language models have various reasoning biases that are not identical to human reasoning biases. So it doesn't guarantee that you won't have those biases, but I think that if your resources are more abundant than humans, you might not need the heuristics that humans resort to.
Yeah, I want to add on a quick point to Tal's point. I think like in that work, they kind of showed that when you kind of keep the same kind of like syllogistic or logical structure, but change the like lexical items such that they either like are consistent with or violate our kind of like world knowledge, then like humans and models will show kind of like content like effects. And I think that as models get bigger, those kinds of effects, if anything, they might get even bigger. I don't think they would go away, right? Because like in the text generated by humans, we're going to talk about things that are consistent with like the physical world, right? Like seas are bigger than puddles. And so I think like as models get better at predicting the next word, if anything, those biases will just get more and more ingrained. So yeah, it's not clear to me that getting better at next word prediction would get rid of these biases in an interpretable way.
Right. And I guess to me, I would add a little bit about like the social aspect of the biases. So I think some of the causes for the biases could also be social. So for example, there's this phenomenon called over-imitation in social learning. So you want a human teacher teach human students to do a task by demonstrating how to do this task in a very complicated way, but there's actually a simpler solution to finish the same task. Human students tend to mimic the exact same, very overly complicated plan. But if you do that with like, for example, a primate, like a chimpanzee, they won't do that. They'll probably figure out the easier way to finish the same task. So there's definitely a biases in this case, and it's not because we cannot have the same cognitive capacity as chimpanzee, but it's because we are more social, because we believe that when teachers teach you something, they have a reason why they do this in this way. So that causes this over-limitation phenomenon.
Yeah, I think there's a lot more that all of us are thinking about in this regard. But since we're already way over the original time, maybe we can go ahead and wrap up. I don't know if there's any kind of final kind of closing statements or closing thoughts that anyone wants to make on this kind of enterprise of cognitive AI benchmarking, the floor is yours.
I guess I can say something here. So I think one thing that's very important is communication. So for example, when I talk to computer scientists, they may have this kind of stereotype towards cognitive science is that cognitive scientists are working on toy examples that cannot scale to real world problems. Why do we even care? For us, I think for most of us here, we understand the importance of cognitive science, but it's not a general knowledge that are shared by people from different fields. So I think there should be an effort for educating people, or a better word, communicating with people from different fields to show the benefit of having this knowledge about cognitive science.
No more thoughts, but thank you for organizing this. This was a very interesting set of talks. The other two, not mine, I mean.
Thank you,
Yes,
Tal.
thank you.
Thank you, Jen. Thank you, Tinman. Yeah, and we'll see the rest of you at or some non-overlapping set at the Cognitive Science Conference in Sydney.
Yeah.
Right.
Great.
Thank you all.
Thank you.
Bye.
Bye.